My name is Simon Cogon. I'm an Airbus expert in UQ&M. And I've got a more general presentation today, looking at some of the challenges. So within engineering and aircraft in particular, UQ&M applications are important to this, enabling the reliable achievement of robustly performing products and services. It's a very nice statement. I would say typically successful applications of UQ&M have been for relatively well-bounded problems, where you're able to sufficiently simulate or test the system of interest and identify the uncertainties, and they are relatively controlled. That's where we've had significant success. However, some of the things that I'm involved in at the moment is looking at UQ&M in the early design phases, and there are still some very significant challenges of this for complex, long lead time engineering products. So aircraft is an example, but anything that is a complex, long lead time product. So one of the key ones is this impact of a timeline of multiple design decisions. Design is not done in one day. You don't design your aircraft in one shot. You design it over a series of decisions over a timeline. So this has quite an impact on how you formulate your uncertainties and what aspects of the design you need to be confident of at different phases. So as I mentioned as well, it's very much dominated by epistemic uncertainty, with limited ability also to simulate the full complexity. So even though the uncertainties are also epistemic, you can't simulate the deterministic parts, the physics, the complex interaction is really difficult in the early phases. You can't do it all. And one of the other ones is that UQ&M is ultimately a capability to provide a better quality of information to enable human design decisions. Computers do not design aircraft, humans design aircraft. So it's a key point that whatever you do in this, it has to be adding value to a human-based decision. And a human therefore has to understand and believe the results that are coming forward, and that's an important one. How do you validate some of this uncertainty? How do you ensure that you are actually giving the right message? It's not an easy question to answer. So this is a slide I've shown a bit before, but an important one. So if you look at uncertainty over the overall aircraft design process, everything from the early phases in the design space exploration, when you're understanding what product to make, right through to the entry into service and operation of your aircraft. So one of the key aspects is that the design uncertainty reduces through the phases, but so does your freedom, your design freedom to correct any issues that you've built into the process. So the freedoms you have in the design also reduce as your uncertainties reduce. So we have kind of two main areas of this, and they're kind of separated by a particular point in the aircraft program. So in the early phases, it's very virtual. So you haven't made anything. So it's prediction, uncertainties, and target setting. So you're looking at all of the different potential technologies and topologies of your aircraft that you want to bring together, and seeing how confident are you that I can make an aircraft and that will perform well enough to be sold, that there is a market available. And there was a point in the process, in fact, I might as well introduce it now. There's a point in the process where we actually offer the product. So there's a product offer point in the process. This is a really key point in the design process because it fundamentally changes how the uncertainty problem switches. So before this point, you're very much virtual. So your aircraft doesn't exist. It's all virtual. You've not made any commitments. You are free, therefore, to continue working on it, to continue to improve, to analyze, to reduce your uncertainties. But at a cost, the more you kind of do this, you're spending effort. But at some point, we actually offer the aircraft to customers. We start selling it. And we sell that aircraft well before we finish designing the aircraft. We certainly haven't made anything. We haven't even finished designing it yet, but we are selling those to customers. So customers in aircraft, like several years before we've made the first one, we have signed contracts. And this is important. So as an example, if we miss our block fuel, our fuel consumption metric, our guarantee, if we miss that by 1%, we pay $2 million per aircraft. for every aircraft that still fails that criteria. Okay, so that is big money if we get that wrong. So there's a real balance that as soon as we've made that offer, the problem changes to how do I ensure I can make my design commitments that I've commercially committed to. So the problem changes then into what is the best aircraft I can make in a very kind of global sense, to now I need to deliver something to some contractual commitments, and what levers do I have available that enable me to meet those commitments. And it's a really big distinction in the program for me. What I'd like to introduce now is this kind of concept that the aircraft timeline is actually a kind of a function of design levers. So this concept that you don't design everything in one go, you have kind of various levers that you are able to use in the aircraft design process. So in the very early phases, these levers are very kind of large. So you're dealing with things like, in the very early phases, even your kind of requirements. So the range, okay, the range and capacity is almost the requirements. What aircraft do I think I can sell? This is something you're playing with in the early phases. What are the different options of different types of aircraft? Once you've converged on those, you have, what does my aircraft look like? How big are the wings? How big is the fuselage? And what are the different technologies I want to bring, different engine technologies that are available? So this kind of cascades down throughout the time where you go into more and more detailed analysis later in the process. And we're trying to bring some of these earlier in the process, but typically, you know, for example, you can't be still designing your flight control systems when you're still haven't decided how big your wing is. There is a dependency on this. You can't do the really detailed designs really early in the project because you don't have sufficient definition of the aircraft. So this is also important when we start looking at uncertainties. So in the early design phases, we typically have to try and lock some of the early kind of aspects of the aircraft design. So what is our current basic configuration to enable you to start going to the details of aerodynamic shape optimization, structure optimization, aeroelastic manipulations, and system design. So you can't do it with everything open. So this timeline is important, that it's not a one-off decision where in the early phases you're expecting to simulate everything. You can't. And this is an important part that, for me, it's in the early phases, you're not trying to design an optimized, reliable aircraft. You're trying to ensure that the selection of your design parameters gives you sufficient confidence that you can design an aircraft that will meet your performance guarantees and be certifiable and safe. So you're not doing the full design, you're trying to position yourself that you have sufficient freedoms available that you can exercise these levers to achieve your goals. And this is an important distinction. And also in the early phases, there are many links between these levers. So as you set some of these levers, you can impact how much freedom you have later in the design. So as you fix certain aspects of, say, your wingspan or your wing area, you put constraints on how much freedom your later levers have in your structural optimization and your loads alleviations. You start putting in limits on the level of freedom of these levers. So this is also part of this timeline of decisions. So before I go on to looking a little bit into what that means in aircraft, I want to give you a generic example along the terms of mitigations and contingency. And what does that mean? So simple example, conference travel plans. So I think everybody here has been in this. So you need to get to an important conference. You cannot travel the day before. You're giving the keynote speech and you need to arrive on time. So this is a remote location, local train runs every 2 hours. So there's a high risk that you might miss that connection. Okay, typical stuff that we deal with every day. So if we talk about a mitigation, this is something you can do later if you need to. So for example, in this situation, you could get a taxi. So if you miss the train, you just collect a taxi. Fine. Question would be, at what cost does that mitigation no longer become a good option if you were paying? we're claiming this. So at some point, that mitigation, it's there, but that cost of the mitigation becomes something you don't want to spend. Secondly is the idea of contingency. And in reality, going through some of the philosophy of this, there's a bit of a grey area between the two. But for me, the contingency is a provision for a future option that you need to protect in the current decision. So as an example of that, a hire car. So for example, there may be a big event in the city and there's a limited availability of taxis. There's a high chance you won't be able to get a taxi. You could get a hire car, but you need to pay a non-refundable deposit today on an option that you don't want to use. So say you'd rather take the train, maybe because you haven't finished your presentation for the keynote speech. I'm sure that's never happened to anybody here. But this is something that you don't want to take that option, but if you really think it's risky, you may have to pay that up front. And this very much relates to the decisions we make in aircraft design, where we have to assess the different risks and the different options, and sometimes we build in contingencies for things that are not optimal, but we believe we may need to achieve some of the key performance metrics of the aircraft. So with that generic example, I wanted to take a little look at this kind of idea of this design convergence timeline, where again, this is not a single decision, but we have a series of decisions along the timeline of the aircraft. So if we look kind of the levers along the bottom, we have a decision today that we need to set some of those levers to meet a certain performance metric, that red line. So if we look at where we are today in terms of our current current assessment of where the design is against the performance metric, we're a little bit below the target. So if we look at almost a classical uncertainty, so we look at all the potential uncertainties and things that could happen, we see there's actually a very low chance of achieving that. However, an important thing to note when we're looking at uncertainty is that aircraft design is not passive. So it is not a passive system. We are actively trying to achieve that performance metrics. We have lots of clever engineers, and we have lots of these levers available to us to try and pull those levers to mitigate and to achieve our performance objectives. So if you look at that yellow curve, this is almost, or the yellow area, this is almost trying to an idea of, okay, we have a large amount of uncertainties, but because it's active, we are able to reduce that through our design work over time. However, you can still see there's a very low confidence, even with the mitigations, of achieving that final performance metric. So typically what we do is we would kind of set those levers and we would add a margin. So we would kind of set those levers to a point where we are now more confident of achieving that performance metric. And if we look at an example of a typical design path, and it's not, there's many different forms, you can see that as we go through that, in each of those red triangles where we have future design decisions, we have an opportunity to exercise those levers to mitigate any performance degradation that we see and to do something to get back on track to meet that performance objective. So we have future mitigation options and potential contingencies that we can call upon in order to get back to our performance metric. So this is really important in the early design phases of considering not just in today's decision, you need to consider the impact of future decisions you will be making on what you do today. And this is a really important one. It's not a one-off decision. You need to know that you have future options to do something which impacts what you do today. But obviously it's not that simple. So the more complicated reality from that example is, in fact, we have multiple different performance metrics and constraints in a design space. There are many. That red line is simple and one simple performance metric. And there are differences in these constraints as well between hard constraints, so kind of certification requirements and safety, or key performance objectives which you can't sell the aircraft. So a certain range target. If you don't meet a range target, nobody's going to buy your aircraft. And the difference of that is soft or tradable constraints. There are some constraints that are not mandatory for the customer. They add some value, but you can trade them away. Or you can trade, for example, one of the classic ones that we do, say your performance on your fuel versus your manufacturing or your recurring costs. So this is typically what we've done before. We will make our performance, so we have a well-performing aircraft, but often at the expense of, it's really difficult to make, or we actually don't get enough of the industrial impacts in that. We've pulled the levers to meet our performance, but now we're not making enough money on the aircraft because we've built in lots of complexity that shouldn't be there. So these trades go on all the time. In fact, that diagram on the right-hand side there is a little bit what Peter was showing earlier, this kind of idea of constraints with an uncertainty band. So this is something we're working on at the moment in the early design phases. This multi-dimensional approach of objectives and constraints, each of them is uncertain, and now you're picking a point in a design space of where you have the most confidence of meeting your different constraints. And again, some of those are hard constraints, cliffs. If you don't meet them, you're screwed. And some of them are, no, I have options to mitigate or trade or just not meet them because they're not as important. It's a very complex ball of different things that you're trying to do. And also, each of these levers that we pull doesn't just impact a single constraint. So every time you pull one of those levers, typically you're impacting multiple different objectives and constraints with each one of those levers. So a simple example there is wing tip twist, where if you kind of twist up your wing, you can change the drag and the mass of the aircraft, and they are opposing. So they are that same lever has opposing impacts in your two different constraints. That's a simple example, but many of them are much more complicated than that. So these uncertainties are largely epistemic, at least in the early phases, and it's very difficult to quantify these from experts. So expert elicitation processes are not easy. We've been through several of them. They are not easy to do. And it's also very complex and difficult to simulate the full complexity of aircraft design in the early phases. You have kind of lower fidelity, lower complexity methods, but you're not going right into the details of full, flutter calculations, air elastics calculations, everything else in the design phases, because you can't afford it, and you don't have enough definition of the design even to build some of those models. So, in complex systems, what is the right level of detail to simulate in order to make your decisions? So if we say in the early phases, we're interested in our block fuel, our fuel consumption of the aircraft, what is the uncertainty on that prediction? Well, you could ask a load of experts. You could just say, okay, what's my uncertainty? You get them at a table and you say, okay, can you quantify that uncertainty that you have today based on the current knowledge of the aircraft and your previous expertise? Now, an expert would typically go, well, actually, I know what drives block fuel. I can break that down into the three main elements of the weight of the aircraft, the aerodynamic drag, and the engines, the fuel consumption of the engines. And you also have some way of simulating the relative impacts of each one of those on the fuel, kind of the overall aircraft size and process. And you can, and this is something I've been through quite recently, doing this exercise in Airbus. But each one of those, in fact, has further elements. So you can go infinitely in detail to break any one of those down. So we look at mass, we have the structural mass, we have the systems mass. On the structure, it's a function of the loads, the sizing optimization, the loads alleviation, air elastics, and lots of other complicated things. So you can go and work out at each and every one of those levels and propagate the uncertainties back up to your block fuel. But you get more benefit from doing this. So the more you can do that, the more benefit of capturing the complexity, but the harder it is to do, and the more it costs you in terms of simulations. With a key challenge, as Peter mentioned before, of dependence. So both statistical dependence and the dependence in the actual simulations itself of the design processes. This is not an easy question. And this is something that in the early design phases is very difficult to understand. What level of simulation do you need to go to ensure that you meet your requirements sufficiently? And it's an open question because I've been through a little bit of this exercise already at the top level, and there are many things we're learning, I can say. So bringing that then to a bit of a kind of summary and conclusion. So there's this continuous drive to improve the performance of engineering products. And UQNM really is a key enabler to help us understand how to make our decisions in the design process to achieve this reliable achievement of these robustly performing products and services. In terms of the challenges, a proper mathematical formulation of how we deal with uncertainties over a timeline and how we include future design decisions or the impact of future decisions on today's decision is very interesting to me. I've never seen that properly formulated in anything I can understand. And how to understand the key driving uncertainties and where to focus the subsequent efforts. So you can't focus your efforts on everything. So a lot of what we do in Airbus is you try and find the things that are driving your design. You do sensitivity analysis, you find the things that are most important, and you look to try and understand those. But you may potentially be missing ones that suddenly pop up later that you haven't considered. And then finally, as I started, I think in the first slide, it's really important to remember that whatever you do applying UQNM to the problem, ultimately it is a human, a chief engineer and architect that makes these decisions. Mm-hmm. Computers do not design aircraft. They provide information for engineers to make design decisions. This is really important. So UQ is just a better quality of information on the risks to enable humans to make those decisions. And humans will have uncertainty as well. The whole human decision process is uncertain. Humans come with knowledge, with constraints, with baggage, if you like, from previous aircraft programs. There is a whole aspect that I've got in my mind of the uncertainty of the decision-making process and decision makers, in addition to all the complex design uncertainty. Okay, I think that was it from my side, and that's my favourite T-shirt that I haven't got with me this week. But thank you. You can read that. Any questions from anybody? Can we get any part?
So in the Airbus design practice, when you reach design freeze, I can use that concept. Do you have a process for quantifying the uncertainty regarding, is in existence now a process for quantifying the uncertainty on the design parameters?
I would say not categorically in terms of the uncertainty. It's done inherently in engineers looking at sensitivities, but not, I would say, we don't come up with intervals or probability distributions or anything like that. It's more engineering judgment of what are the risks. So there might be kind of a risks and opportunities, which is a form of uncertainty, but not kind of proper, I would say, categorization. We are starting to.
And I guess the DAWS project is trying to inform that. That's my understanding.
To help a little bit, yeah.
Thank you. Another question.
Yes.
So you described very nicely, Simon, the timeline in the design process. And I think there's also another timeline in the acceptance of UQ methods.
Yes, there is.
And I wonder how far along that timeline you think your company is.
That's a good one. It's gaining momentum.
Yeah,
it's definitely gaining momentum. For example, internally, I have one of the senior architects that is now very much wanting to see uncertainty distributions on his selections of aircraft configuration. So it is growing. It is growing. I think it's not, I would say, Airbus wide or industry wide in this acceptance, but there is definitely a recognition that this is something that we should be grasping.
And so I would say that engineers have a good understanding of what safety factors are, and there's generations of engineers who've worked on this and have come to accept safety factors. And there's got to be the same level of trust in UQ techniques that there has been in the past in safety factors.
Yep.
So it's really a difficult thing to achieve that when there are so many, a myriad of uncertainties that you have to consider.
Yep. And it's actually a very, very difficult question I'm battling with at the moment. How do you validate your UQ1, especially in early design? I would almost say these are unvalidatable. You cannot validate your early design uncertainties without building 100 aircraft in parallel with engineers that don't talk to each other and looking at a statistical distribution of what came out, which is not going to happen. So you can invalidate, but you can't validate.
Sure.
General, the truth.
Yep.
For model validation as well.
Yep.
You can invalidate your model, but you can't really say for sure that it's valid.
Yep.
Can I first and reverse specification?
Yes. Yes. So all of what I said today was probably more the uncertainty in being able to meet the current certification rules, but then there is also uncertainty on how do we challenge those, how do we challenge the safety factors. Okay, I've got this one.
Yeah, we have a. Can we have one more question from Philip? Yeah.
Yeah, maybe one question picking up what Garrett said. You spoke about the UQ and the design and the acceptance of it. And if there is a process, the way I get it, it's, let's call it forming in a polite way.
Yep.
Can you comment about the process on sensitivities? Because I believe at the end of the day, sensitivities is going to be what the decision maker, or what ultimately helps the decision maker to not follow something he feels is right, but to can make an informed decision on sensitivities. Can you comment on the current status there?
Yes, so I would say sensitivities is something that we do, and we always have done. So you always look, if you have a key design decision and you're not sure, you will do some analysis on the sensitivities of that design to your parameters. But it's a bit kind of, I would say, focused on specific areas. There's not kind of a bigger picture of looking at the uncertainties on all of your constraints. You're trying to focus on specific areas of risk, and maybe other things then come back and bite you because you haven't really assessed all of those elements.